Um, a vector field is, well, in 2 dimensions, or 3 dimensions too, but what you're going to do is at each point, so a vector field is going to be a function, and we're going to start off with big F with the vector symbol there above it. Big F, so a vector field is going to be a function, but it's going to be a function that assigns a vector to each point. So each point, that assigns each point, x comma y, a vector. We're talking about 2 dimensions. And that's going to be vector form, so it's just our normal vector form there, but this is what the deal is. The function changes at each point, changes the vector. The best analogy, and you don't see it as much maybe anymore, but the best analogy is like on a weather map for wind speeds. Sometimes you'll see different vectors. Maybe they don't put, well, I guess they do arrows, but you know, kind of think of a coordinate system here. But say at this point, I've got this vector, and then it comes over and a little different vector, and then maybe it switches around. It could do all sorts of things. So may not be quite that complicated, but well, they do switch. But at each point, you're just assigning a vector, you know, magnitude and direction. That's what a vector is. It's a directed line segment, if you will. But anyway, that's what it's going to do. Each point is not just going to be a point, it's going to be a vector. Okay. So that's what a vector field is. It's a function that gives you that. All right. Now, in kind of generic form, the function, the vector field function looks like this. So it's a vector, so it has an ij component if we're talking 2 dimensions, ijk if you have 3 dimensions. But each, instead of having a number for your vector, each component, it's a function of x and y. And of course, you could write it the other notation way of writing. They probably usually use this, but remember, you can write vectors different ways. But yeah, so that's why it's a function, because each part is a function, and each part describes, you know, the component. Like I said, if you went to 3 dimensions, you'd add x, y, z, and then you'd have an I, j, and then k component. So the parts here, the p and the q, those are sometimes referred to as scalar functions. You see that term, that's referring to those parts. Okay, so let's do one. All right, so f of xy equals 1/2 y, it's an I component, minus x j. Okay. And, you know, this could be, here we're just going to sketch with the table here, using the table. We're plugging in x comma y, so we're plugging in different points. And so, yeah, there's infinitely many points we can choose from. So here's some ones I think. All right, let's start with 1, 0. And so here, on the second side of the table, we'll put what our function is. So if I plug in x to be 1 and y to be 0, what does that leave me? What kind of vector does that give me? Well, since y is 0, that part's 0, and then that part is -1. All right. So let's just start the sketch here and think about kind of how we maybe graph it. I don't know if they give you the values to use here, but so what this is saying, at the point 1, 0, let's kind of make it pretty wide. So at 1, 0, this is our vector, 0, -1. So 0 in the x, and then -1 in the y. So that vector would be at that point. Okay? So that you just get point by point, you just get the vector. All right, and so I guess what I did start off with, I just kind of went kind of in a circle. All right, let's do 0, 1. 0, 1. X is 0, so that part would be 0. The j component would be 0, and the I component would be a half, right? Half 0. So at 0, 1, I'm at the vector, or the vector I have at 0, 1 is a half comma 0. So half in the x, 0 in the y. So that would be here. So just kind of go around kind of in a circle here. So let's do -1, 0 next. So x is -1, so that would make that +1, the j component, and the y component is still 0, I component. So at -1, 0, I'm at 0, 1. So x is 0, y is 1. This one goes up. And then complete the circle here. Let's do 0, -1. And so that would be x is 0, so that would part be 0, and -1/2 would be the I component. So at 0, -1, I'm at -1/2, so it'd be backwards a half, and then 0, y. So you can kind of see, we're kind of putting together a little vector chart. Yeah, let's do some kind of more interesting one. Let's do 1, 1. Because that kind of gives me a little different feel to it. At 1, 1, I'm at, well, both the x and the y are half, so both the x and the y are 1s. So that'd be a half for the I component. And then -1 for the j component. So at 1, 1, right here, I'm going x is a half, but y is -1, so down here, right? So yeah, you get some of that angle off there. What be another good one? Yeah, so let's do a couple more. 2, 0, 0, 2, and 2, 2. said, I don't know exactly how many of these they'll want, but so at 2, 0, x is, so it'd be 0, and x is 2, so it'd be negative 2. And then 0, 2, so the y is 2, so it'd be 1 for the I component, and 0 for the j component, and 2, 2, so I'd have 1, negative 2. So those three, at 2, 0, which is right here, I have 0, negative 2. So yeah, you kind of get the idea here that some of these vectors are going to be longer, some are going to be shorter. That one's 2 units long. All right, 0, 2, which is here, I'm going 1, 0, so x is 1 minus 0, so just straight across there, and then at 2, 2, x is 2, y is 2, I'm at 1, negative 2, so x is 1, down 2, yeah, another angle 1, and so, you know, if you, you kind of keep it going, just to cut to the chase here, this one kind of goes like that, you have another one kind of like that, go out a little further here, so, yeah, you kind of see, it's kind of swirling around. You get different information from it. But if it's a wind map, yeah, we kind of got this little spin going here, don't we? Anyway, they're kind of interesting. But. All right. Now, one other point to this, okay? Recall gradient vectors. Remember that? Remember the gradient vector, what it was? So recall with me the gradient vector. So if we had a function of 3 variables, x, y, z, the gradient vector, which we use the upside down triangle, I guess is kind of what it looks like. Gradient f. Remember what it was? It was the vector, and the components were the partial derivatives. The I component was the partial derivative with respect to x, the j component was the partial derivative with respect to y, and since I'm doing 3 variable one here, the k component was partial with respect to z. Remember that? Well, isn't that a vector field? So this is, this is a function of x, y, z, this is a function of x, y, z, and this is a function of x, y, z, theoretically. I mean, they may not have each part, but each of those is a function describing the component. So a gradient vector can be considered a vector field. The gradient vector field, okay? And now our new terminology, okay? So we've got ourselves a vector field, we didn't even know it, okay? So let's find the gradient vector field. For f of xy equals x squared plus y squared. gradient vector field is just the gradient. So we do the partial with respect to x, partial with respect to y. All right, so this one only has two components because I'm only dealing in x and y. So what do we got? What's the partial with respect to x? 2x. Partial with respect to y? 2y. Okay? All right. There you go. Okay, now, a quick little point using this one as our example here. Okay, so this is our function, and this is our vector field. If I graph this, some level curves. Okay, let's sketch the contour map, let's call it, level curves. And the gradient vector field. And we'll use f of x, y equals k for the contour map. K equals 1.5, 3, we'll go by 1.5s here. 6, all the way out to 13.5. That's what I did. And I've already done this for you, so don't get too excited here. You'll have to get something out here. I've already done this. Okay. But here's a couple of things to note. So I've got it sketched on the paper here. One thing to note is notice the contours and the if you can find one where you've got a contour touching a vector. Do you notice something about the contour in that vector? Think about the tangent line to the contour map, the actual vector there. Like right out here, it looks like it's about 2.5 as far as the x and y is concerned. Yeah, oh, for one thing, yeah, if you do these contours, yeah, you get circles, right? Because if you plug in 1.5, that's going to be, well, it's a circle of square root 1.5 radius. So yeah, you just got the contour maps are circles. But one thing we can point out is like, got one, I think it's about 2.5 there. And then this, there's a vector, I thought there was one, yeah. Well, maybe it's, anyway. One of those circles you can see, or several of the circles you can see one of the vectors touching. Well, do you notice a little perpendicularity going on there? Yeah, the vectors are going to be, always are going to be perpendicular to your contour. That particular contour. Okay, so that'll always be true. Anywhere you have one of those touching should be perpendicular. Another point, though, is, okay, so first point is, these are equally spaced by 1.5 as far as k goes. But do you notice something about the progression? So 1.5 is here, except the radius is the square root of 1.5. And then the next one's a little further out. And then one thing you'll notice, and it's probably not quite this evident. But the distance here, the contours are getting closer together. Well, if you have any knowledge of map reading, like a topographical map, what does that mean if your contours are getting closer and closer together? It's getting steeper, right? The change is greater. So when our contours get closer and closer, okay, so the closer contours, that means your graph is changing more. So that equals greater change. And so, yeah, in this case, the greater change happens. I haven't got it exactly all drawn out here, but they get tighter and tighter the further out you get. So this graph is getting steeper, if you will, the further out we get. Which if you think about it, so these are levels. So z equals this equals this equals, so you're getting bigger circles, but they're going up quicker. You know what I'm saying? It's getting steeper. So the closer the contour, so on a contour map, the closer the contours, the greater the change in your function is. So that's one thing. Now, do you notice something else about the vectors as we get out further? So in here, they're little bitty, little small little vectors. Further and further out you go, they get wider. So guess what the greater change equals in vectors? Larger vectors. So larger vectors mean greater change as well. Again, to make the analogy to the wind map, yeah, the longer those vectors are, the higher the speed. So anyway, so there's some interesting things that can come out of just the mapping. We won't do a whole lot of those because, yeah, they take a lot of time, but they're interesting. All right. So the last thing for this section that I wanted to cover with you is to talk about the conservative vector field. So a vector field is conservative. Vector field F is conservative if there exists a function, little f, such that our big F vector field equals the gradient of F. So we talked about the gradient vector field, but if we've got a vector field and it turns out it is the gradient vector of some function, it's called conservative. Now, that would mean then there's some functions out there that are not conservative because they don't have a function that they equal as far as the gradient is concerned. And again, just a little terminology here. The little f is called the potential function, or a potential function. Okay. So a vector field is conservative if it's the gradient vector field for some other function. For example, and we'll talk about how you find these later on, but a few things to go over before we get to that point. But just to give you an example. F is equal to yi plus xj. that's conservative. Because since f of xy equals xy, is your potential function. And the gradient, notice here, what the gradient of f is here. What would be the gradient of f? Remember, the gradient of f, partial with respect to x, partial with respect to y as our components. What's my partial with respect to x here? Y. Partial with respect to y? X. You notice what that is? Isn't that f? Because f is yi plus, I mean, it's the other form here. Okay? So there's an example. This is conservative vector field because it has this potential function right here. Okay? If I change one little thing though, make it negative yi plus xj, that one is not conservative. We said we'll talk about how we can verify that, prove it or whatever. There's just no way to get a gradient, to get a function whose gradient is that. And sort of would make sense if you think about it, because yeah, what are you gonna, if this right here gives me that gradient, how am I gonna get, what is this one, negative y comma x? So how am I going to get a gradient where it's, instead of yx, it's negative yx? Because you can't do negative xy, because negative xy would give you negative y negative x, right? You see what I'm saying? It's going to be hard. You're going to have a hard time there. So, anyway, just for right now, know what the term conservative means, and we'll play more with that later on. All right?